All right, good morning, everyone. I forgot to put the link yesterday or to share the link yesterday with our current units. So we're starting chapter 7. I just put that link on the chat box. I also sent out a remind. But at the top of that page, you're going to see textbook links to textbook problems for homework, but also you'll see the calendar, March calendar. Well, it's basically March today, last weekday of February. But you'll see the calendar. You'll see CalChat link for solutions to all the odd numbered problems, as well as on my website, just like how before I organized everything by date. So you'll see the notes, you'll see worksheets, you'll see links to class videos. So I just want to spend a bit of time just kind of going over what's coming up, and also just reminding us that we're getting close to or near the end of our semester in terms of getting to this being our final new unit. So today and Monday we're going to focus on area between curves. So we've been dealing with area sort of, well, for the most part, with integrals, but sometimes we've been getting some negative values, right? And we knew that regions below the x-axis was negative, regions above is positive, but now we're going to be able to have a formula that will ensure that we're always getting a positive number, and that positive number will always represent the area of a specific region. So we'll spend today and Monday going over those topics, or this specific topic of area between curves, and encourage you guys to bring in your calculator or have access to them. Ideally, I think Graphing Calculator is going to be visually more helpful. We can find more in this 36 Pro. We can do a lot of things with it, but it does have its restrictions. Some of the things that we're looking for may be more abstract. But yeah, ideally 84, but we can get away with the 36, and I'll show you how we can arrive at some of the values that we can do that we do with the 84 with the Graphing Calculator. All right, so we'll spend today and Monday going over that, and then Tuesday we're going to start volume by this method. So 7.2, it's just one section, but we're splitting up into 3 days, or into 3 topics, into this method, washer method, and volume by cross section. So just volumes of different shaped objects, different orientations. We have circular shaped objects that have no gaps. This is based around axis of symmetry or axis of revolution, where there is a gap, like a bowl-shaped object or a ring-shaped object, and then cross-section, where we're building different shaped objects on top of a known base. It could be a triangle base, or rectangle base, or trapezoid base. Okay, so we'll have a day to review this method. We'll have a day to review washer method, and then we'll do cross section, and then we'll have 2 days of test review, and then we're going to get that test in before we go on break. Well, for you guys it's break. For us it's teacher work day. So after we come back after that extended weekend, then we're going to be in review mode. So we know that the AP exam is going to have a free response section, and I think it's going to be 6 free response questions. If it's the same format as not last year, but in years past, And with those 6 free response questions, we kind of know what topics we're dealing with, but there's going to be some variations in terms of how they explore each of those topics. But I like to be able to kind of take the time to maybe focus on 2 or 3 topics, and then we'll have a quiz over those 2 or 3 specific types of problems, and then after that we'll have another week to kind of get familiar with another 2 or 3 topics, and then we'll have a quiz over that. Okay. And that second FRQ quiz, we're looking to be that Thursday right before spring break starts. But just as a reminder as well, that Tuesday before spring break is ACT day for juniors, so it's asynchronous day for everyone else, but we'll be administering the ACT for juniors in school on that day. Now, after spring break, we're going to be preparing, still reviewing, but we're going to be specifically preparing to take the pre-AP test. So we're basically going to be doing a mock AP exam, kind of helping you see the scope of the full exam. We may take it over the course of 2 days potentially, and it'll be worth 2 test grades. Okay, but it'll be curved like the AP exam, so the curve is pretty generous. And after we take that, then we'll have an idea as to what to expect on the AP exam. And after that, I think we'll take that pre-AP test probably mid-April, and then we'll spend the last week of April kind of going over it. And then when May comes around, that first Tuesday of May, I think May 5th, you guys will be taking the AP exam. Okay. Now, I don't know what exactly the AP exam is going to look like. I have a feeling that it's going to be more like what we saw in years past with free response and multiple choice. So it's, I think, most likely it's going to be that, not like last year where it was just 2 free response questions and just 40 minutes. It's going to be more the extended AP exam. But right now, I don't know if we know for sure whether it's going to be in person or whether it's virtual or whether it's a combination, depending on the student. But ultimately, College Board is letting each school make that determination, make that judgment call, what's appropriate for each school. They're allowing each school to do what's best for that school. And so for us, our AP coordinator is Ms. White, and so she's going to be the one. I think right now she hasn't made a decision yet. I think she's still kind of gathering information, but ultimately she's going to decide for our school whether it's going to be in person or virtual or maybe a combination of both. But we'll just kind of wait and see what that's going to look like. All right. So, any questions? So yeah, so I think that's pretty much going to be the last thing that we do. Once we get past the AP exam, then I don't know if I have anything else for us after that. Any questions for this unit or what's coming up that you guys have right now? Okay, so let's move into our notes for today. Okay, so today we're talking about area between 2 curves. A lot of it is going to be recognizable because it's basically just the integral of a function. But now we're going to have a formula that is adapted where we're no longer having to stare at a negative value. Sometimes I would say, oh, this integral is negative, it's area related, but it's not quite area because of the negative. But now we're going to be able to ensure that we're no longer going to get a negative. We're going to get a positive value each time we put it through this formula. So we have two separate formulas or two orientation, same equation, just different different orientation. So the first orientation is what I call the vertical orientation. This is where we can imagine the region between two graphs being above each other. And if they're above each other, we can think of it as stacking vertical rectangles from one end to the region of the shaded region to the other end of the shaded region. So we have a formula that can help us find the area of something that is in this orientation. So you can, if you guys can do this here, you can draw a vertical rectangle that represents what these rectangles are going to look like. We're essentially stacking infinitely thin rectangles, vertical rectangles, from one end of our shaded region to the other end of the shaded region. So our area formula calls for the bounds, so x1 to x2. And let's say those bounds, right now it's general value as a to b, but let's say it's x equals 1 to x equals 4. We need to identify a graph on top and the graph on the bottom. And basically, it's just whatever is above and whichever is below. So we see that the f of x is obviously above g of x, at least for the shaded region that we are concerned about. And another way to think about this is look at what is hitting the top of the rectangle and what is hitting the bottom of the rectangle. Okay, what's touching the top of the rectangle is the f of x, so that's another reason that we call it the top function. The bottom function is g of x because that's what the bottom of the rectangle is hitting, is touching the g of x. So we can start putting it into our formula. So our area of the shaded region for this graph, definite integral from our bounds, from left bound to right bound, from 1 to 4. Top graph minus bottom graph, so f of x minus g of x dx. We started this semester talking about approximating a region using rectangles, right? And we did Riemann sums, we did trapezoids as well. But essentially, all those rectangles is just width times height, right? But then we moved on to the fact that we can add up infinite numbers of rectangles using our limit definition, and then we're able to even get cleaner from that by just using definite integral to avoid all that algebraic step. But I want to remind us that technically there's also a width and height component within these definite integrals. So the f of x minus g of x, when we subtract that distance for a specific x value, we're arriving at the height for that particular rectangle. And so we can think of that f of x minus g of x representing the height component. And then the dx is just representative of the width component. So we do have a little bit of that width times height represented within this notation. So area is width times height, and it's kind of built into our definite integral formula. Okay. Now, something else I want to bring up, and this is going to become more apparent on Monday, and also moving forward when things get kind of moved around and it's not clear which orientation, and just being able to know the separation between them or to distinguish between them. All of our expressions, if it's a vertical orientation, everything that we see needs to be in terms of x. Our expression is in terms of x. We have dx to represent that everything we see is in terms of x. Our bounds are in terms of x. Our left and right bound is in terms of x. So if we want to do a vertical orientation, that means a graph is above the other one. We're always going to be relying on this top minus bottom formula. Now, your expression is always going to be in terms of x, but then more generally, we can say that your equations will always take on the form of y equals. Whatever is to the right side of the y equals is going to be ready to be inserted into whichever portion of our formula. Sometimes I say in terms of x, as a general statement, but then at the same time, not every expression has an x in it. Like it could be a constant, but that constant is always going to take on the form of y equals. So if you see y equals, you know that expression is ready for your top minus bottom orientation. Okay. Now, example 2 is just to show that sometimes, or a lot of times in the past, we never had to talk about the bottom function, right? We just identify the function and we just put it into the integral. But actually, there's a bottom function that's hidden from view that's always been there, but we just kind of always ignored it. Right? Because normally we just say, okay, the integral from a to b of f of x, right? But technically, there's a bottom function that's hidden. We see the top of the rectangle is touching the f of x, but what's the bottom of the function touching? Yeah, y equals 0. So we always ignore that y equals 0 because it's always the same thing and it's always just disappears from view. But I just want to show that even with a definite integral notation we've seen in the past, it technically is a top minus bottom. We just always, we haven't been talking about it until now. But if I want to set this up, I can technically think of it as integral from a to b, top function being f of x, minus the bottom function, which is 0. So normally when we talk about integrals, we always talk about in relation to the x-axis. So that's why it ends up being disappearing because of the 0. So here we have the top function and 0 being the bottom. But we always have that. We always have the 0 just disappearing. So that's why we usually associate with just integral of f of x and nothing else. Okay. But now moving forward, we're going to have something that is not just always, it's not going to, our function is not going to be paired with just the x-axis. We're going to have more variation. We're going to have a bottom function that is distinctly different. Okay. But I want to give another quick example here. Let me call this example 2b. Is, let's say I had a graph that looked like this. Okay, there's my x and y axis, and let's say I had a graph that was below the x-axis, and I wanted to find the area of a shaded region between, let's say, 1 and 3. And let's say this function is called g of x. We see the shaded region. We see the boundaries of the shaded region. We see that it's paired with the x-axis, and we can see, we can draw a representative vertical rectangle that connects the distance between them. So if I want to find the area, I can use the formula that we've been using. So how would you enter this in? Integral from where to where? Good. Yeah, a to b, but in this case, it's 1 to 3. Okay. Okay. What's the top graph? What's the top function?
0.
Yeah. So you see, if you look at the rectangle here, it's touching the y-axis. Sorry, the x-axis, which is y equals 0. Minus, what's the bottom?
The bottom function.
G, yeah, g of x. And if we put it through this formula, we can ensure that we always get a positive value, right? Because g of x is an accumulation of negative values, but this minus sign in front of it is just going to take care, it's going to revert all those negatives to be positive. And if we put it through this formula, we're always going to be able to get a positive number in return because we've adapted to the fact that our region is below the x-axis with that negative sign. Oh, let me just give one more quick example here. Let's say I had, let me call this example 2c. Let's say I had a function f of x that was clearly above the x-axis. And then I had another graph that was clearly below the x-axis. and I want to find the area between these two graphs. Let's say it was from 1 to 6. Okay. Same process, area equals depth integral from 1 to 6. What's the representative rectangle? Being a vertical rectangle that connects the two boundaries. What's the top graph? Okay, minus q of x. Okay, so yeah, for some of you it may seem like a very straightforward thing, but I think some students want to overcomplicate it. They think that they got to make some adjustment for the region that's below the x-axis, and they got to involve a negative sign and changing the sign and involving the x-axis. But we don't have to worry about that. Right? So whatever the top function, whatever the bottom function is, there's a change in sign below the graph, but everything is going to be taken care of by this formula. So there's no need to overthink it. You don't have to worry about, okay, this region is below the x-axis. Do I have to involve the x-axis or not? No, as long as we have the top and bottom function identified, you're good. Everything will work out. That region will be adjusted below the x-axis. Okay. Okay, so let's look at a full example, a specific example using functions where we have to work things out by hand, and also we can plug in the calculator as well. But we're going to practice using the formula, this top minus bottom relationship there between the two curves. So first, we see that we have y equals x squared. We see we have y equals 2x plus 3. We have the enclosed region, which I'm going to shade in, but this is the enclosed region is what we're going to try to find an area for. We see that these are both functions. These both take on the form of y equals. So you see that y equals form. That's matching exactly with what we need for a top minus bottom orientation. So let's label what we see here. Y equals x squared, that's going to be the parabola. Y equals 2x plus 3, that's going to be the linear graph. We're going to connect the two graphs using a vertical rectangle as the representative rectangle. I'm doing things a little bit out of order here. I'm going to identify the top and bottom function first. We see the top of the rectangle is touching the linear graph. So, you know, this 2x plus 3 must be the top graph. The bottom of the rectangle is touching the curve. So we know that must be, the x squared must be the bottom function. Okay, so we know which one is the top, which is the bottom. We know how to start putting into our formula, but something that's missing that we still need are the bounds, right? We don't have x1 and x2 yet, at least not, we kind of guess because everything is labeled, but we're gonna have to find these intersections. Now, when we find these bounds, we can find them by finding the intersections between these two graphs. If you can see that the intersections of the graphs is exactly where the boundaries are going to occur. So we're going to set the equations equal to each other. When we set them equal to each other, we can find those intersecting points. When we find those intersecting points, they will identify for us the bounds that we want. So imagine we're basically stacking vertical rectangles from this end all the way to the other end, right? And they're obviously all different heights, infinitely thin, but we're just basically stacking from one end to the other. We need to identify where those endpoints are. So the way we do that, we're going to take our two graphs, two functions, we're going to set them equal to each other, and we're going to solve for x. Okay. So set equations equal. And this will help get us to our bounds. Okay, so x squared is equal to 2x plus 3. We'll bring everything over to one side. We'll set it equal to 0. so that we can factor, we can solve for x. Okay, so we ask ourselves what multiplies to be -3 and adds up to be -2.
X minus 3x plus 1.
Mm-hmm. Good. Solve for x. 3 and -1. Okay, so these are the exact values that we need for our bounds. If you look at the graph, it kind of makes sense as well. Right? You can imagine this value to be -1. You can imagine this other intersecting to be 3. Okay. Everything that we need is ready for us to put into our formula. So area equals, area equals def the integral from lower bound or left bound to right bound. We start at -3, we're going to 3. The top graph being the 2x plus 3, that goes first. Minus the bottom graph. Now this is a good habit for us to start practicing, is always protect the bottom function with a set of parentheses. In this case, this particular problem is not going to make a difference, but later on we may have multiple terms as the bottom function. If you don't have a set of parentheses in place, you're going to lose track of the negative in front, and it's going to cause your answer to be off. So let's go ahead and try to get into that habit of always putting a parentheses around the bottom function. We really don't need it for the top function because it's always a positive. I mean, you can, but the sign is never going to be, it's not going to be influenced. It's only going to be influenced from that minus sign in front of the bottom function. Okay, so top function minus bottom function. Right now, let's just do this by hand, but we're definitely going to practice entering this in our calculator, but we can do this by hand, right? These are just terms that we can apply power rule for. Okay, I'm purposely leaving out the bounds as a way of reminding myself I got to take care of the antiderivative first. These are all power rule terms. So 2x becomes 2x squared over 2. 3 becomes 3x. X squared becomes x cubed over 3. We're dealing with definite integral here, so there's no need for plus c. No need to adjust the bounds because we didn't do u substitution, so we're ready for our bounds. Okay. Do a little bit of cleanup. I'm going to take remove the 2's. Okay, which value do we enter in first? Yeah, upper bound, right? So upper bound always gets evaluated first, so that's right, upper minus lower. So upper first in for all the x's. Minus, and we want to have a big set of parentheses for lower bound because of the minus sign in front. Okay, so we combine all these numbers together. You can use your calculator, but ends up being area equals 32 over 3. Okay, if it's a calculator section or if it's multiple choice with calculator, then your answer choice may be something like this, where you have to work it out by hand. But if it's free response and if it's non-calculator section, you can leave your answer unsimplified and they will not take off points. So this is completely acceptable. But if you just stop here, that's not enough, right? So we need to see, and the graders need to see how to work those bounds in, right? So, but if you stop at this mess, this is acceptable. These are equivalent. It's just not as clean, but you won't lose points. Okay. Any questions working out by hand? Okay, so let's practice entering this in the calculator. I mean, we know how to use integral notation here in the calculator, but let's just get that practice in. So you're going to go to Math 9. I'll show it on both the 84 and the 36 Pro. You're going to go to Math 9. We'll enter this integral into our calculator. So we'll do 2x plus, first the bounds from -1 to 3. 2x plus 3 minus parentheses x squared, close parentheses, dx. You can do the math fraction button, math 1. Take you from a decimal to a fractional value, 32/3, just like what we were able to find. And at 36 Pro, same thing. There's that integral notation there, second e. (32/3). Okay. Also, I'm going to have the calculator find the intersections for us. We can do it with the 36 Pro, but right now, today, I just want to talk about how we can do it on the graphing calculator. So if you have a graphing calculator, just follow along. We're going to enter both these graphs into our calculator, and then we're going to look for those intersecting points. We're also going to play with the with our window as well. So go to y equals, enter in your function. We're going to enter in x squared and 2x plus 3. And now we're going to graph it. Now, when you graph it, you're going to do zoom 6. If you do zoom 6, doesn't mean that's the best place for our graph, but it does kind of reset our graph to a starting point, and then from there we can decide, all right, do I need to make any adjustments? But it kind of centers our graph if you do zoom 6. So once you entered in your function under y equals, then you're going to zoom, and then you're going to go to option 6, zoom 6. Okay, hit enter. It'll take you to a -10 by 10 window. And then from here, I want to look for the intersecting points, but I can kind of tell that it's not very clear up here. It looks like it's getting cut off. I want to see my graph kind of come out the other end after they intersect. So just want to kind of show you that we can adjust the window manually if you go to window. If you go to window, you can play with Xmin and Xmax and just kind of push your what's being shown above and below, but don't play with this the scale. You're just playing with the Xmin and Xmax. So for my graph, I want to see a little bit more above, so I'm going to play with the Xmax. I'm going to push it out to 15. I can obviously just play with other values if you like. 15 or 20, I think is good. You hit graph again, and now it's going to extend my vertical a little bit, to the point where I can kind of see what's happening beyond that intersection. Kind of gives me assurance that that I found that right point. Okay, so that's just a tool that I think is helpful, especially if you just wanted to see just a little bit more than what the graph is showing you. You can adjust your window. Another thing that's good is being able to create a box that will help us zero in on the parts that we are only interested in. So let's say I want to just create a box around just this region where I'm seeing here, where I'm seeing a little bit beyond my intersection, so I can kind of see it clearly. So I'm going to go to zoom, but you're going to choose zoom box. If you choose zoom box, that means we're going to create a box around the region that we care about looking a little closer at. So hit zoom box 1. Now you're going to see a blinking cursor. So you're going to move that cursor to where you think you want the corner of your upper corner of your box to be. So I want my box to be here. So I want my upper corner to be somewhere in this region. Okay, hit enter. Now, when you hit enter, now it's basically putting that cursor down on the graph, and we're going to be able to draw our box from here. So don't hit enter anymore. You're just going to use the directional arrows now. So I'm going to move my arrow, extend it to where I want it to go. So don't hit enter. So you're going to drag down that line, and that box is going to begin to form. And I want to see a little bit below on either side here. Okay. Now, when I hit enter again, it's just going to zoom in where I see in the box. Hit enter. Okay, so now I've got a very clear view of my intersections. It's fairly zoomed in. Now I'm going to look for my intersecting points. Okay, we solved by hand to be -1 and 3, but I'm going to work. We're going to use the calculator to find it for us. Okay, so go to second trace. It'll reach that calc portion. Oops. And we're going to choose intersect. So second trace will take you through calculate, and then we're going to choose intersect. Okay, so this is going to help us find the intersection. Okay, the calculator is going to ask you for a first curve. Okay? It seems obvious, right? There's only 2 curves here, so it should know. But if there are multiple curves on the graph, and we want to find the intersection, we want to tell the calculator which graphs to look at. So my first curve, I'm going to label it as the curve, but you want to put it in a specific location. You want to put it relatively close to where the intersection is, not on the intersection, just somewhere close to it. So I'm just going to pick a point that is pretty close. Either doesn't matter which side, you can choose it on this side or on the other side. Maybe it's easier for you to see it if I move it up here. So relatively close to my point of intersection, and hit enter. So now it's locked in. Now the calculator knows, okay, you want me to look at the curve. Second curve, you should see a blinking cursor that shows up on the other graph. And then again, you can choose any point on the graph, just not a point at the intersection. You can choose a point relatively close, and we'll move it here, make it easier for you to see. And once it's relatively close to the intersecting point, hit enter again. And now the calculator knows, okay, you want me to look at the curve, and you want to look at the line, and it's going to say the word guess. So now the calculator is going to look for the closest intersecting points between those 2 identified points on the 2 graphs. Hit enter again, and it's going to find that order pair for you, -1, 1. So we only care about the x value, and there's -1. Okay, let's practice finding the intersection for the other at the other end of this region. So do second trace, intersect again. You're going to scroll your graph, your cursor to a point that is close to the intersection. Hit enter. It's going to ask for a second graph. It should be blinking at the other graph. Hit enter again. And then when we enter a third time, it's going to find that intersection for you. 3. Okay. Now, what you don't want to do is you don't want to put your cursor directly at the intersection. If you put your cursor at the intersection, it's going to confuse the calculator. It's not going to know, wait, is that the first graph or the second graph? So don't find the intersection for the calculator. Let the calculator do it for you. So choose points close to it, and the calculator will find the intersection. So if you try to find the intersection by putting it directly at that intersection, it's going to confuse, and it won't get you the answer that you're looking for. Okay, we'll definitely practice more with this, but at least to kind of get our feet wet with some of the notations that is going to be helpful and useful for more involved problems. Okay, let's go to the back page, and we're now going to look at the orientation of graphs that are not necessarily above each other, but across from each other. Still the same formula, but we're going to have to flip everything kind of sideways. So now we're looking at 2 graphs that may not necessarily be functions. And if that's the case, we are still going to find the area between the 2 graphs, but then the orientation is no longer going to be vertical rectangles. Now we're going to be thinking it in terms of we're stacking horizontal rectangles above each other, not to the left and to the right of each other. So you can tell that these graphs are not functions, right? These graphs do not pass the vertical line test. So we have to adjust our equation a little differently. Now we can imagine, though, because they're across from each other, we can draw a horizontal rectangle that connects the two graphs. So let's go ahead and do that first. So this kind of gives you some visual idea of how the area is going to be found. It's going to be essentially stacking these infinitely thin horizontal rectangles from the lowest of our bounded region of our shaded region all the way to the top. So that's where the bounds come in. The bounds tells us how low to start and how high to end up. So we go from y1 to y2. These are all y values. For our example, let's say this c value is y equals 1. And for our example, let's say that's this d y value is 5. So notice everything is in terms of y. Our equations are also in terms of y. Notice that our expressions that we're using will be in terms of y. And our form is going to be x equals. So if we see equations as x equals, we know the right side of that expression is ready to be inserted into our formula. So we can tell that the right endpoint of the rectangle is touching this graph on the right. I'll label that as the right curve. And you can tell the left endpoint of my rectangle is touching this other curve, which is the g of y. So I'm going to call this the left curve or left graph. Now we can just create an area notation for this problem. So definite integral from lower bound to upper bound. So from c to d, but for this problem, I just made it more specific from 1 to 5. Right graph minus left graph. So f of y minus g of y. And don't forget your notation to finish the notation by saying that is dy with respect to y. Okay. Again, we have our height components, but our height is kind of horizontal. And we have the width component. Okay. It's still there. It's still area related. All right, so let's look at a full example where we have two graphs that are not oriented above each other, but across from each other, to the left and to the right of each other. So we have two equations here. Notice the equations is looking a little different. First step is we have a function here, but this curve is obviously not a function, right? It's not going to pass a vertical line test. And so, but the equation is nicely set up for us to apply this right minus left. They're both in the form of x equals. I'll write this a little bit larger here. So x equals 1/2 y squared minus 3. Okay, I'm going to draw a representative rectangle that connects the distance between them. You can imagine we're basically stacking infinite numbers of these horizontal rectangles from the lowest point to the highest point, and they're all of various heights, but they're infinitely thin. Okay. So I'm going to label the the y plus 1 as the graph on the right, because that's what the right endpoint of my rectangle is touching. And the left endpoint of my rectangle is touching the curve, so that's my left graph. Okay, so we have our left graph and right graph identified. We're going to be using this formula that I have at the top of the page, but rather than, so I don't want to shift the graph, my paper up and down here. And now let's go ahead and find those bounds. But the bounds that we're looking for are no longer x's, they're going to be in terms of y, but our equations are set up where we can easily find the y's. So we'll set the two expressions equal to each other, and then we can find those intersecting points, and those intersecting points will indicate for us the bounds of our region. So I'll say 1/2 y squared minus 3 is equal to y plus 1. I'm going to get it ready for factoring, so I'll bring everything over to one side. I know that 1/2 y squared looks messy, but we can deal with that. So minus y. Combine like terms. -3 minus 1 is -4. I want to factor, but I don't want to deal with that 1/2. So if I strategically multiply everything through by 2, I can kind of balance out my equation. I can multiply everything through by 2, which will get rid of that fraction, but I'm balancing it on both sides of the equation. So I get y squared minus 2y minus 8 equals 0. Okay, factors nicely. Multiplies to be -8, adds up to be -2. -4 and +2. Okay, we solve for y. We get y equals 4 and y equals -2. And you can tell by looking at the graph that makes sense, right? We see our lowest y value being -2. We see our highest y value being 4. Okay, so now I think we're ready to insert everything into our formula. Our area, we have a right minus left orientation now. Everything that we're seeing is going to be in terms of y. Our equations are correctly set up as x equals on the left side. So depth integral from -2 to 4. The graph on the right is the y plus 1. Minus, now we definitely need the what? Parentheses. Yeah, if we don't have parentheses here, it's gonna throw off your answer. But hopefully we can just kind of have that habit of always including a set of parentheses for that bottom function or for that left function. Okay, so our left graph is the 1/2 y squared minus 3. Okay, make sure you finish off your notation by indicating the dy. And now, I mean, we can do this by hand. This is all power rule, but we'll just go ahead and make the calculator do this for us. If you want to go back to your home screen, do second mode. It'll take you out of the graphing screen that you're on. And also something else is you may be seeing different variables on paper, but in the calculator, you're always using x. Okay, don't try to match the variable that you see on paper. It'll mess things up. Your calculator will complain. So just always use x for any variable that you're doing, regardless of what you see on paper. So math 9, depth integral from -2 to 4, x plus 1 minus my left function. So parentheses. Now you can use math, the alpha y equals, which will take you to math print. You can do 1/2 there, but I'm just going to convert that 1/2 to a 0.5. Okay, dx. Okay, you should be able to get the same thing on your scientific calculator on your 36 Pro. Area equals 18. Okay, any questions here? Okay, one final example, example 5. It says, represent the area of the shaded region to the right using integral notation. These are both functions. So we're going to be able to use the top minus bottom orientation, vertical rectangles. But what do you notice about the shaded region and about the top and bottom function? Okay. And what do you notice about the top and bottom function? Is it consistently the same?
Like on the left, it's the top function is the x and the bottom is the linear.
Yeah, the linear. So basically, we can't rely on just one integral. If we rely on one integral, we don't have a consistent top function that extends from one boundary to the next. So if you see that there is a reverse in order of your top and bottom function, that's going to tell us that we have to rely on two separate integrals. One integral to represent one region with that specific orientation, and then we need a second integral to represent a flipped orientation between the top and bottom function. So let's do that. I'm going to draw a representative vertical rectangle connecting the boundaries. The curve is the f of x. The linear graph is the g of x. So okay, let's do this. Let's do the left, the smaller region first. Okay, what are the bounds going to be from where to where?
From 1 to 2.
Yeah, 1 to 2. Right, everything's in terms of x, right? We don't look at any y values. Everything's in terms of x. Okay, the top graph is the curve, so it's f of x minus, we see the bottom of the rectangle is touching the line, so that's g of x. Make sure you complete that notation there with a dx. Plus, so we have one region represented. Second region, what are the bounds?
From 2 to 4.
But now my top function is what? Yeah, so you see that my top function is no longer the curve. My top function has all of a sudden switched over to the diagonal line there. So g of x now comes first, minus f of x. That represents the height component. We have the width represented by dx. So now we need both integrals to help us find the true area of both these regions added together. Okay, any questions? So on Monday, we're going to be exploring, kind of building on top of this topic. We're going to be looking at some free response questions that require a little bit more effort in terms of getting the forms correct. Because right now, everything, the form is nicely set up for us, but we may have to, everything may not be quite set up as nicely. We may have to do some algebraic resets, or we may have to get everything in the correct places before we can look for our bound, before we can plug into the formula. So we'll practice with those types of kind of extended problems on Monday. Okay. And I may adjust the notes for Monday. So yeah, so try not to, if you want to print it out, try not to print it out until Sunday night. But hopefully I can get that in this weekend. All right, thanks everyone. Hope you guys have a great weekend. I'll see you Monday.